Welcome to the Contagious Code Podcast, where we dive deep into code, learn practical skills, celebrate the beauty of engineering, and eliminate imposter syndrome. I'm Tejas Kumar, and I've been building on the web for over 20 years at places like Vercel, Spotify, Zeta, and many more. Today on the podcast, my guest is Shivay Lamba. Shivay is an international conference speaker and an expert on WebAssembly and using AI in the browser via WebAssembly. Shivay has been active in a variety of ecosystems from Python to the web to others. And our discussion today is great because it's multilingual and multi-framework. In fact, in this episode, I learned that WebAssembly isn't unique to the web. You can use WebAssembly as a runtime for Python, Rust, and other things. And because of that, it lends itself well to redistributable AI workloads. If all of these words are confusing, let's just take a moment and demystify. WebAssembly is just a way to run assembly or machine code, usually in some type of web runtime, like a browser or Node.js or similar. You can see now how this is important for running AI workloads in a distributed way, meaning on any kind of device. Any device that ultimately runs the web, like a browser or something, now has access to machine code compiled binaries, like machine learning models and inference engines like VLLM, Olama, and others. If you're new to AI and inference and these kinds of things, there's other episodes of the podcast about AI. We encourage you to find them. In any case, today Shivay walks us through exactly that: WebAssembly and distributable AI that is private and secure and on device, so that your users don't send their data to some foreign provider where they don't know what's happening with their data. That's the gist of our discussion. Of course, there's a lot more there. And so if you're interested in engineering AI, WebAssembly, or the web platform, this episode is for you. Before we actually start the episode, I'd love to emphasize, hey, this episode is separate to my day job, and the way we can sustain it is through partners and sponsors. If you're interested in partnering with a podcast or sponsoring it, then find me on X, formerly Twitter. There's links in the show notes. The Contagious Code Podcast is partnered with Code Crafters. Code Crafters is a phenomenal way to level up your coding skills. The way they do that is by having you choose a programming language that you're interested in and a tool that developers use, tools like Git, Redis, Docker, etc. And what they do is they have you literally build the tool, like build Git in the programming language that you chose, like Rust, Julia, R, Python, JavaScript, whatever. And by doing this, you get better at the tool because you understand like how it works, and you get better at the language because you use it to build the tool. You know, it's a great 2-for-1. They have a generous free tier. If you want to start paying, you get a massive discount if you use the link in the show notes that also supports the channel and the podcast. That's tej.as/codecrafters. Thank you so much for sticking around. Here's my discussion with Shivay Lamba. Shivay Lamba, welcome to the podcast.
Thank you so much, Tejas. It's an honor to be here. I know we have known each other for quite a while, and I've just been so encouraged to look at each and every single podcast episode that you put out because it has some of the most uh, technical discussions that I've seen. I look at a bunch of different podcasts and listen to them, but the kind of discussions that you have, they are completely unfiltered, raw, and sometimes there's such great deep dives. And they also tell the other aspect of the user who appears in that podcast episode, right? It tells about their story and how they became successful in whatever they do. So thank you so much for inviting me. And I'm super excited to having this conversation with you today.
Yeah, I'm really excited. You've been doing some really great work, WASM, AI, and running like machine learning workloads, and there's a lot to talk about.
Yeah.
Before we do that, indeed, I really enjoyed meeting you as well at so many conferences. That's why we're doing this. But man, I've had this burning question for so long. Your name Lamba means tall, right? Like it means Shiva is tall. But you're not. I mean, you and I are similar height. I don't consider myself tall.
Yeah.
Tell us about that.
No, I think the word lamba in Hindi or lamba in Hindi, yeah, it means tall, but I don't know. I mean, I feel a lot of times when we look at our parents, typically their children are taller. My dad is like 5 feet 11, and I'm 5 feet 8, so I'm actually not taller than him. Maybe because I growing up, like I feel I was active in sports, but probably not in the kind of sports that naturally help you to grow taller. I mean, I had a
Yeah.
good diet. Like my mom is a dietitian, so I don't think so I had any lack of nutrition. But maybe I was not that active in the kind of sports that make you taller. I don't know, like scientifically, I feel I at least should have grown taller than my dad, but that just didn't
Yeah.
happen. But I think I think God or maybe like nature has been kind to me in other ways apart from
Yeah.
height.
Yeah, yeah. It's interesting because so many times the people whose names people's names tend to fit their profession, right? Like what
Yeah,
was it? The CEO of like Starbucks has some type of brew or some type of coffee. Anyway,
brew.
but yeah, there's this whole like trend where your name kind of lines up with your vocation. Anyway, that's just a little icebreaker. I was so curious about that. Let's I want so I've divided up this episode. I did a lot of work, and by me I mean my agents. Did a
Hmm.
lot of work preparing a nice structure today, and I'd love to sort of have a discussion in maybe three or four different topics. Topic number one, WebAssembly plus AI. I think that's really your field of expertise, and I think there's a lot of value there. Topic number two, machine learning in the browser. You've done a lot of work with TensorFlow.js, and I think people
Yeah.
would be interested in that. Number three, RAG techniques, LLM apps. You've done some work there as well, right? And so, and maybe if we have time, I'd love to also pick your brains on DevRel and developer communities. So I think those are the four things I want to hit on. And depending on how we go for time, I think that's kind of what I think the audience would enjoy, but honestly I would also enjoy. With that, let's maybe start by one of your recent passions, combining WebAssembly with AI and machine learning. You gave a talk at, I think it was WASM.io,
Yeah.
titled Privacy First, Building LLM Powered Web Apps with Client Side WASM. What's that about, and why does it matter for developers?
Yeah. So I have been a huge advocate for WebAssembly, and I know that you have also been into the ecosystem for a while. I saw one of your talks probably from 2018 or 19 when you had
Yeah, that
used
was
WebAssembly.
yeah, it was 2018.
So
Sorry,
2018.
2019 in Romania. Yeah, yeah.
Yeah. So I know like you have also done a bunch of work, but I certainly feel that because of the fact that earlier there's this misconception about AI being limited to large scale GPU clusters or maybe just these Python developers who don't like to get out of their shell. But we have really just seen the last like 6, 7 years that the proliferation of AI into other means. So that's whether it's the browser or even on the edge. We have seen a lot of AI being used in all of these edge architectures or edge
Wow.
use cases, right? And primarily, if you look at how that has happened is because we have been able to not only optimize these AI models. Now, of course, that's a completely separate discussion, but the way that you will actually run them is thanks to technologies like WebAssembly that is capable of being able to run your workloads in the browser or even on the edge. So my area of interacting with the WebAssembly has actually been luckily on both the browser side and on the edge side. Now, specifically, like because you mentioned about the talk
Yeah.
and why it actually matters to people is the fact that a lot of companies today, they or individuals, they are really focusing on privacy. Now, one of the things that everyone probably, or not everyone, but a lot of people know is that these LLMs, if you're using like OpenAI or Gemini, they actually might end up using your data to further train the models. And from time to time, you always see that sometimes some private information has surfaced up, whether we talk about DeepSeek or there's this really famous case of Samsung researchers where one of Samsung's proprietary code or maybe documents surfaced in a random search query with ChatGPT. For companies that are privacy conscious, they don't want to send their data to the LLMs. And also, it's very costly, right? Of course, only recently we have seen the cost per million tokens reduce quite considerably, but just about 6, 7 months ago, it is very high. So for companies that are conscious about their privacy, about their costs, they can run these LLMs on device. And we know that web is the biggest platform. So it naturally makes sense that we can incorporate these LLMs or even AI applications that can natively run on the web, probably as part of your browser, so that even if you are not connected to the internet, or even if you are, then you can still have all of your data, whatever you're doing, whether it's running some type of RAG application or maybe you're doing some text generation, all of that can sit in your browser and can natively run without having to connect to a remote LLM, because that also then helps you reduce the latency because all of the inference is happening right there in the browser. And the primary technology or the stack that you look at would be WebAssembly and Web GPU. So we can probably talk about Web GPU later, but WebAssembly will be the main way, because if you look at JavaScript, while it's great for the ecosystem, it is one of the most versatile programming languages. I know you love it, I love it, but we know its limitations, which are when it comes to a lot of high compute, it is not necessarily the best. So that is why things like video editing in the browser, you would probably want to offload that. And WebAssembly as a technology allows you to bring functions that are written in other programming languages like Rust, Python, C++ to go ahead and execute in the browser. So that means you could offload the most compute intensive part of running model inference, which is the actual mathematical compute, whether it's like doing matrix multiplication over millions of vectors. So all of that can be offloaded uh, thanks to WebAssembly. And this way, your WebAssembly would interact with JavaScript, and the inference will be done thanks to whatever code you're running. So that's the model inference code, and you'll be able to get your results right in the browser. So my talk was mainly like talking about making people realize that yes, privacy is important, and at the same time how they can use these browser technologies like WebAssembly, and giving them some examples of how you can actually incorporate the WebAssembly backend for a lot of these machine learning models and leverage that in your web app to create these performant but still secure applications that can run completely in your device.
Interesting. Thank you. That sounds like an amazing talk. We'll put a link to that talk in the show notes. Absolutely. You mentioned so many interesting things here that I want to double click on. Specifically, let's first understand WebAssembly. I know what you mentioned was WebAssembly is a way to take binaries from that were compiled or created in other programming languages like Go, Rust, Python, maybe. And I don't know about Python because it's dynamically typed. But in any case, you get a binary from some foreign language. You can wrap it and run it in JavaScript. And therefore, in JavaScript runtimes like the browser, Node.js, Bun, Dino, etc., that's cool. So that allows interoperability, and WebAssembly also runs code like directly on the machine, as far as I know. Yeah, it doesn't run it in the browser runtime, and you pass messages between sort of WebAssembly and the runtime. Is that all accurate so far?
Yeah, absolutely.
Good. Okay, so then you mentioned Edge, running AI inference workloads on the edge. I'm well aware there's people listening to this that maybe don't quite get Edge, because we talk a lot about the cutting edge, the bleeding edge, the network edge. There's a lot of Edge. Edge is the I think the bass player from the popular rock band U2. What do we mean running AI workloads on the edge here? Can we double click on that a little bit?
Yeah, absolutely. And I know that the definition of edge might vary from person to person, but what I specifically wanted to convey was more about these low power devices. So that could be a phone, that could also be a Raspberry Pi, or you could also go smaller than that, because we have been able to optimize certain machine learning models that can work on anything that's probably a bit bigger than, let's say, apart from Raspberry Pi, you have so many different device architectures like x64, x86, RISC-V based small devices that only have a very few amount of megabytes of compute, right? That's the as low as we are talking about. And of course, you can't expect to run like a large PyTorch or a TensorFlow based model with Python, because if you look at just the size of the PyTorch binary, that's already in huge megabytes. So you need some way to be able to shrink down the model, quantize the model, and not lose a lot of the performance so that you can use them. So a typical example in this case is like, for example, Amazon, right? In their warehouses, they have these CCTV cameras, and they have embedded a computer vision model. So as soon as your item comes in, they will be able to probably use the computer vision to detect what kind of item it is, and it can get added to the inventory. So they usually use it in their last mile or their first mile networks to account for how many items are coming in. Or maybe another example could be one of the embedded CCTV footage that runs on the traffic lights to be able to detect the license plates. And they are also using these really small computer vision models that can detect the cars or maybe the license plate numbers. So that's the kind of edge that I'm referring to, which is these really low powered devices, but still being able to do the machine learning inference on such devices.
On the devices themselves. Wow.
Yeah,
And but these devices don't run JavaScript usually, right? Or do they?
yeah. No, I mean, I guess like there are two parts to this. One is some of these devices could technically run Node.js or even because like Raspberry Pi that supports running Node, right? So that has
Right.
support for Node. So maybe you could ship your WebAssembly, but outside of if you talk about outside of JavaScript, there are still ways to actually run WebAssembly on the edge. So there is this really well-known WebAssembly runtime called Wasm Edge. So you can see right from the name itself that it has specifically been designed to run. So this WebAssembly runtime can be run on any type of device architecture, whether it's RISC-V, x86, and typically, so this runtime has been written in C++, but it's really optimized to take your code that has been written in Rust. Because we know that with the Rust toolchain, you can very easily create your WebAssembly binary from your Rust code using Rust up, right? And then this more optimized Rust binary code that has been compiled to WebAssembly can now be run.
Mm.
So usually you will see that there are more use cases where your if you and there is an example of TinyGo. So like TinyGo can today compile into WebAssembly, and now you can run that on the edge as well. I'll make sure to probably share with you some examples. There is this person called Roy Evans. He is one of the TinyGo maintainers, and he creates some of the most insane demos. So, in fact, he created a demo for the WASM.io conference where he controlled a drone with the help of a controller, where every single button in the controller was linked to a TinyGo function, but it was actually executing WebAssembly. So whenever
Wow.
he clicked, like let's say, button to make the drone go up, that's a function in TinyGo to, of course, to make the drone go up, but it's actually executing the WebAssembly on the drone itself. So
Mm.
you can see like there are so many different optimized ways to run WebAssembly on the edge, not just with JavaScript, but I think with another way to also look at this is that we usually look at V8, right? But there is also this really small not WebAssembly, but JavaScript runtime called QuickJS. And QuickJS is really small and tiny, and you can actually also use that to execute JavaScript on the edge and run WebAssembly with it.
Right. So you don't what I what I'm hearing you say is you don't need necessarily JavaScript to run WebAssembly.
Yeah, you don't need necessarily JavaScript. So especially like
What?
yes,
But
on
it's
the
called
browser, yes.
WebAssembly.
Yeah, that's the confusing part, right? So originally, if you look at the origin of WebAssembly, it did start as a browser first technology. Like I think the origin is, if I recall correctly, is the ASM.js, which was the
Yeah, right.
assembly from the folks at Mozilla back in, I think when they started working on this in 2015, 2016, I guess.
Yes.
That was like the original intention. And yes, I think there has been a lot of debate around why do you use the term web, where truly WebAssembly is a global technology, right? You can run it anywhere. You can run it in the cloud, in Kubernetes, in the edge, on JavaScript. In fact, we have seen that over the past few years, there have been more use cases for WebAssembly outside the browser than in the browser. So yes, I mean sometimes I also debate that why have we kept the term WebAssembly, but I think because the origins were on the web, and eventually it found its path. People realized its value on the serverless on the server side as well.
Man, that's so interesting. I had no idea. So all you need is a WebAssembly runtime, not necessarily a
Yes,
JavaScript runtime, and it
exactly.
runs in the runtime. Wow,
Yeah.
that's I'm so surprised. I guess naming things is hard. That's why we don't have it. So you mentioned JavaScript is not good at doing high compute tasks, like and this is why you offload a lot of the work to WebAssembly. Why is that?
That's a good question. Maybe would love to also pick your brains in that, but I guess it boils down to the fact that if you look at the raw performance of something like C++ versus like even Python. Now we know that the original Python has been based upon C Python, which means that it's like based the underlying architecture of Python is also like with C. So
Yeah.
one could argue if I just like use a brute force way of explaining this would be that because it's built on top of C Python, that's one of the reasons, like architecturally, why Python is not as performant as the low level C, C++, right? And in a similar way, if you look at I guess like with JavaScript, and please like correct me if I'm wrong, because I might not be the best person to specifically answer this from an architectural perspective, but um, if you go to the more low-level architectural languages like Rust or C++, generally because you are interacting directly with the bytecode level, right? You get much more performance. Now, that being said, that doesn't mean that JavaScript does not do that. Ultimately, you take any programming language, you go through that path where you write the high level source code, but it goes through the path of then whether it's with Java with the JVM, where you create the bytecode and then you execute it. Maybe like that's one of the reasons why it's not as performant, because there are more of these steps involved. And please correct me if I'm wrong.
First of all, this isn't a job interview. I think and this is an expectation for you to like answer
Yeah.
correctly. I don't think you're wrong, right? I think just if I reason about this from first principles, JavaScript is a language that first of all runs in a runtime.
Yeah.
And the runtime does things like manage memory and allocate
Exactly.
memory and free memory. And also the runtime does a lot of optimizations for you, things like tail call optimization, etc. And all of that is intermediate software that is between you and the metal.
Yeah.
And it's honestly, it's between you and the CPU. And so even if you were to write something like Rust that has no intermediary step but runs directly on the CPU, it
Yeah.
still wouldn't be enough, right? For machine learning / AI workloads, because you need high parallelism, and
Yeah.
CPUs suck at parallelism compared to the CUDA architected GPUs, where
GPUs. Exactly.
it can do calculations like millions of them in parallel. Whereas CPUs just they can do parallel tasks, they're just not optimized for it. And so
Yeah.
I think if I consider my own question, I think that's kind of where we would lean. And of course, if anyone knows any better, please leave a comment. I mean, this is very much a discussion.
Yeah.
So you mentioned one of the benefits of running language models directly in a WebAssembly runtime is it solves quite a few problems. For example, user data privacy. You mentioned like sometimes like the Samsung case where like some confidential stuff just came out of ChatGPT because people were using ChatGPT with confidential stuff, and then it somehow made it back into, I don't know, the memory, the training data. ChatGPT is closed source, so we don't know how that works. But so what could happen theoretically is I could put my credit card into ChatGPT just to test, and then months, years later, somebody says, "Hey, give me a list of credit cards that work," and ChatGPT does that, and it yields mine because it's part of the data. So running language models directly in a WebAssembly runtime or the browser can mitigate this because they run completely offline. They're not connected to the internet. They're certainly not sending your prompts, your data to like some external vendor like OpenAI. So we see one of the benefits is privacy because your inference is all happening like on the device, similar to what should have been Apple Intelligence. Also, you mentioned some benefits were lower latency because there's no round trip to the internet and back, and it works offline. I'm curious, are those the main benefits? Did I miss anything?
No, no, I think like those are pretty much what I had mentioned. So yeah, it kind
Okay.
of rounds
So
about the goals.
how does one, if somebody wanted to do this, right? Somebody wanted to take like a Mistral 7B or some open source model like that and run it in a WebAssembly runtime. How would they sort of shrink it down so that they can run it on low power, what you call edge
Yeah,
devices?
absolutely. So yeah, the first step is, of course, it's not magic that you can just take a, 200 billion parameter model or these type of models that we never actually recommend to users to use on the device. But
Yeah.
of course, that WebAssembly cannot magically just run it for you, right? First step would be that you take that original model and you would use techniques like quantization. So if you look at what quantization means, we are now dealing with the bits, right? So there are multiple types of quantization techniques. There's 4-bit, 8-bit, 16-bit. So if you think about it in this way, that uh, every single model is, and when I say like 8-bit, that means you have precision up to 8 bits. So by lowering down the total size of the model, but when you still want to retain the capability and not impact the performance, so these type of optimization techniques for reducing the size while still being able to hold all of that information that the LLM has in less number of bits is what the entire or this entire concept of quantization is, right? Where you lower the memory footprint that the model is having, and you still want it to hold as much information without degrading the performance of the model. So most typically you would start with that. You would start by taking a much more or a quantized model, which reduces the size of the model by 100x, or depending on what type of quantization you end up using, whether it's
But
4
what,
bit,
these
8 bit.
quantized models just like exist somewhere? I can go download them, or
Yes, so a lot of
okay.
them will still exist on Hugging Face. So there are, like, if you yourself can actually do this process of going ahead and doing the quantization. But for most of the popular models, there are quantized versions available that you can today download on Hugging Face or any other model artifact place where you can store and
Right. And
store your
Hugging
models
Face is just like GitHub but for models.
for models, exactly. And
Okay.
it's probably the most popular place because most of these big companies like Google, Meta, all of them are releasing and hosting their model weights over there at Hugging Face. So you would quantize the model and you will host it, but it's still not ready to just directly be run inside of a JavaScript environment, because these model architectures have been designed with PyTorch, so they have a Python based runtime, right? So you have to convert them into a format that can run in the browser or with JavaScript. So for example, if we go before LLMs with the landscape of TensorFlow.js, that is, they had this model converter. So it would basically convert your TensorFlow Python models into a format that would be supported with JavaScript, where
Mm.
your original model would be converted into this model.bin format. And this, it's like a JSON file that contains the list of all of the weights of the model. And they have been converted to be supported to run with the JavaScript runtime. So similarly, if you look at today's landscape of LLMs, you have to convert them into a format. Now, there are multiple open source projects that allow you to do that. So there is the Onyx runtime, which is a separate runtime that allows you to run ML inference, and it has its own conversion process. But then there is also something called as MLC, which has this project called WebLLM, which is one of the most popular libraries that allow you to run the LLM inference with JavaScript. And under that it uses both like WebAssembly or WebGPU. So first process would be to take that original transformers based Python based model, convert it into the format. Again, these are usually just one or two commands that you have to run, and you can convert them into a format that's supported. And once you have this converted format, then it's ready to be used to be executed in the browser. And um, when you're running the inference on the browser, you can select the backend. And when I say backend, it's not like Node.js, but the backend the browser would support. Whether it's like, okay, if I'm running a laptop that does not have a GPU, then I can use the WebAssembly runtime. If I have a good enough GPU, then I can choose WebGPU. So now you'll have different versions of of that converted model to be supported for different type of runtimes. Some of them might be WebAssembly based. Some of them might be WebGPU based. And when you define that, okay, this is my backend choice, right? Whether it's WASM or WebGPU, then you would. So first thing would be that you would download and cache that model in your browser. Usually, the sizes of the models can be anywhere between a few megabytes to probably like 1 or 2 gigabytes. So you
Wow.
would chunk by chunk, it would download that model in your browser, and then you'll be able to run the inference. So that's the typical process of taking that original model, first quantization and quantizing it, or if you don't want to quantize, you could always take a smaller 1 billion or a 2 billion parameter model and also directly convert it into a format. Again, thanks to these model conversion tools that Hugging Face provides, MLC provides, or Onyx runtime, they allow you to convert them into the format that's possible to run with JavaScript. And then you would use either WebGPU or WebAssembly as your as the backend for running the inference.
So let's talk about the role of these tools. You mentioned a couple
Yeah.
tools. You mentioned TensorFlow.js and Onyx runtime in JavaScript. If I take a quantized model and I want to run it via WebAssembly, well, I would first have to convert it. You said to these formats,
Yes.
and then I would ultimately in my code perform inference. I would get some prediction, some output from these quantized models. Let's talk about the role of TensorFlow.js or Onyx. You decide
Mhm.
in that process. Meaning, you said I can use Onyx runtime to convert a quantized model to the right format where I can do inference. But then would I do the inference myself? Would TensorFlow or Onyx.js do the inference for me? Like, where's the boundary between my code and the code of these tools or libraries?
Absolutely. Yeah, that's a great question. So, probably like let's divide this into step-by-step discussion on how this happens, right? So we already have discussed about the conversion process that you use one of the conversion libraries, whether it's with TensorFlow.js. So first, also then answer the question about what is TensorFlow.js. So
Good.
TensorFlow.js is a machine learning library that has been optimized to run WebAssembly workloads for JavaScript, right? Originally, it ran on the TensorFlow based architecture. So, TensorFlow is a very popular library within Python, but now it has support for other languages as well. So, it's a framework for designing machine learning algorithms or even neural networks, right? So, a tensor is nothing but a high dimensional array, which has the values that are being stored once your whatever type of data has been converted into a tensor, right? And then
But
you
by high
run
dimensional
operations,
array, you mean an array with many elements,
many
a
values,
long list.
a long list, exactly.
All right.
So you could think, because see, ultimately with machine learning, whatever type of data that you take, whether it's images, text, they all get converted into mathematical format. Now, different AI models will convert the data into different types. You could have a high dimensional matrix, and then you run a lot of matrix operations or calculations, like matrix multiplication, or again, we're not diving or getting
Sure.
sidetracked too much into the mathematics part. Maybe you can discuss that later. But all of these particular data that you have as input data gets converted into this mathematical format. So that is why the term TensorFlow means the tensors. And then you basically create this kind of a directed acyclic graph type structure where it basically describes how these tensors are getting processed. So when you're actually running the mathematical compute on top of it, how that affects or changes the tensors, because the output tensors that you get are different from the input tensors. So these output tensors are basically the prediction that has been generated after you have run an entire inference, right? So that's what happens behind the scenes. So basically, the Google team, they took the original Python-based TensorFlow library and made it compatible to run with JavaScript, and that's TensorFlow.js. So at its core, TensorFlow.js has mainly three different ways in which it allows you to interface machine learning models with JavaScript. The first one is the most high level, which is simply taking models from Python backend, right, and converting them into to support for JavaScript with the help of this tool called TensorFlow.js model converter. So it takes the Python model and converts into something that's supported to run with JavaScript. That's the most high level. It gives you the model. You, as a JavaScript developer, don't have to know about the architecture. You just simply get endpoints like model.predict. Go ahead and make that prediction. It's a JavaScript function. That's it, right? You don't have to worry about what's going on behind the scenes. The other way is that it provides you the low level APIs, which allow you to actually write machine learning models from scratch. And so that means that you are actually working on the tensor level.
Mm.
So as a library, that's mainly that it allows you to interface and work directly with these machine learning models. Now, when it actually comes to the inference part, the computation part, that is where the WebAssembly, the TensorFlow.js, the way that the library has been written is that it has support for all of the different runtimes that we discussed. So either you can run TensorFlow.js directly on the CPU, on the bare CPU, or you could run it originally with WebGL, or you could use the WebAssembly backend. So every single model that is running with TensorFlow.js, you can choose between the different backends. So the library is taking care of writing the different connections or the connectors between these different runtimes. So, like for the same model, like a MobileNet model, which is an open source image recognition model, you could run it natively with CPU. So in that case, the library will, based on what runtime you choose, whether it's CPU or WebAssembly, the library will automatically take that specific optimized version of the model that has been optimized to run on CPU, or the one that has been optimized to run on WebAssembly. Because one thing to note here is that if you go like one step below that, okay, you have the model and you have WebAssembly, but how do they run? So ultimately, the model is again, when we say about how the mathematical calculations are happening in the model, right? The inference, how is that happening? It's just a bunch of mathematical calculations. There are these custom ops. So these are, or what we also call as operations. So you can think of, like if you talk about convolutional neural networks. So there's an operation of convolutional, where if you're having a deep learning network, and then you're transferring the weights from one hidden layer to the other, so there is these type of operations. Like, it could be a very simple operation like just adding two things. So that's addition op. So every single runtime has these special operations or ops that the model has to support. So whenever you take one model, you ensure that all of the ops for that model are supported with that particular runtime. So with WebAssembly. So let's say you now you're using TensorFlow.js, you're using MobileNet model, and you choose I want to use the MobileNet model with a WebAssembly backend. So in that case, TensorFlow library, the JS library will take that model and the supported backend, which is WebAssembly, and that is what will now get executed in the browser. So as a library, it takes care of supporting all of these different models and having support for the different runtimes, whether it's WebGP or WebAssembly, right? And the way that it interfaces with the WebAssembly runtime is that um, it will have connections where now, of course, if you think of how you load the WebAssembly binary into the browser and how you stream the responses from WebAssembly to JavaScript. So all of that is being taken care by the TensorFlow.js library. So the developer is not expected to actually write the code of interacting with the WebAssembly module. So the TensorFlow library is actually taking care for you. So it will only automatically install or download the WASM binary for you. So because like these are usually on a on a CDN or somewhere, and you have to download that. So it will do the network. It will take care of managing the network call to download that WASM binary and execute it in your browser. So that's what the library does. And the TensorFlow.js model converter is what is responsible for converting the Python-based model into JS. So very on a similar note, you have these TensorFlow-based models, but TensorFlow is not the only way to actually run models, right? You have PyTorch. You also have Onyx-based models. So Onyx.js, in a way that you can take models that have been originally designed to run with Onyx, it will also then similarly take care of converting them to be able to run in a JavaScript-based runtime. And you can choose between the different backends, whether it's WebGPU or WebAssembly. Very similar to how I kind of described the entire process of the TensorFlow.js. So I had the opportunity to basically contribute to the so basically designing some of these custom ops, as I mentioned. So these are custom mathematical operations that are being used to support WebAssembly as a backend when you're executing these machine learning uh, tasks, right? So I had the opportunity to basically contribute to some of them for the WebAssembly backend. So there is something called as like tanh, which is if you look at like sine, taking sine of some value, cosine, like not sine, and then cos values and tanh. So you would typically use like a tanh during an optimization of your model. So if you look at like deep learning models, you have these activation functions. So there's like sigmoidal function, there is tanh function. So it allows you to change how your model is being trained and how the different weights and biases values in a deep learning network, how they propagate further. So by using a different activation function that changes the behavior in which these neural networks perform. So that is why, of course, you cannot expect that there's native capability for JavaScript to actually run that. So you have to write these custom ops where you write the C++ code, specifically for WebAssembly, and the complementary TypeScript code, because of course it's a library for JavaScript. So you write these custom ops, and then these custom ops will be handy when you are using a machine learning model that requires those particular ops. So every
Interesting.
model will have these dedicated ops based on the model architecture, like, because in the architecture it will run these certain mathematical operations. So that means every machine learning model has a custom set of unique ops that you need to be supported with JavaScript or with that particular runtime. So imagine that as a new machine learning model developer, you are converting the model into JavaScript. Now, in order to execute it with WebAssembly, it's you will have to also do this one pre-step in between where you check all of the ops that are used by the model and whether they are supported with that runtime. If
Mm.
it's not supported, then you have to write those custom ops, and then it will be executable, or it will be possible to execute and do the model inference with that runtime like WebAssembly.
Fantastic. Okay, so the real nuance between TensorFlow.js and Onyx.js is really some models are created to work better with, for example, Onyx.js, and this is when you would use the tool. But ultimately, they do very similar things. It sounds like.
Exactly. So
Okay.
it's just like, how we have different JavaScript frameworks like React, Svelte, all of
Yeah.
these. Again, React, not a framework, but let's say you compare, right? You have all these different frameworks like Solid, Svelte. So similarly, there are different type of model architectures. So some person might use PyTorch, someone might want to use a TensorFlow. In fact, if you look at the TensorFlow library itself, it's kind of now under maintenance mode. Uh, Probably because Google had different strategy with their machine learning, specifically to focus on their Gemini models. So today, I would say like the most popular frameworks for writing most of these LLMs is also PyTorch. So if
Mm.
you wanted to have PyTorch models being supported, then you'll basically like again use the library that converts them into that format, and you can execute. But yeah, the example is like you can use either TensorFlow based models with TensorFlow.js. If you have some other architecture, you can use like Onyx.js, and then there's now MLC.js that again helps you to convert models that have been originally written in like Python to convert them into an architecture that's supported to run with JavaScript.
Right. Interesting. Well, thank you for clarifying. I'm curious. You in your demo, um, you did some great stuff that I won't spoil. We'll encourage people to go watch. But there are limitations, right? If you're doing ML workloads in JavaScript or WASM, there's definitely limitations. You talked about that. You said,
Yeah.
for example, you can't run 200 billion parameter models, for example.
Mhm.
How how can you overcome these? Is the answer to just use a tiny quantized model? Is there some middle ground, or is it literally just that, like use a tiny model and hope for the best? Oh, could developers maybe do something like Apple, right, where they have a local model, or they claim running on iOS, where it's private, it's safe, it's on device, but sometimes you need to reach out to ChatGPT. Apple has this where it'll ask you like, "Hey, can I share this with ChatGPT?" And then you say yes, and
Mhm.
then it defers almost to the bigger model.
Yeah.
Could that be one way of overcoming these limitations? I'm curious about your thoughts on all this and how you can overcome these and how you did overcome them in your demo.
Yeah, I think like that's a very good point, because see, ultimately you are downloading and caching this model on the browser itself. Now we
Yeah.
know that you cannot expect to download a 100 GB model and cache it on the browser. That's just going to be chaotic, right? Catastrophic to be is probably the right word. Um, so yes, there is a limitation of how much. Of course, I think if I'm not mistaken. Today with WebAssembly, the maximum size of any module that you can have is like 4 GB. It will actually expand it. So with the recent WebAssembly spec, now you can load up to 4 GB based uh, artifacts. But you would not expect a person to download 100 gigabytes. That's just simply not fruitful. And see, ultimately, even when you're using WebAssembly, your WebAssembly is executing that on the CPU, or like if you're using Web GPU, it's basically like you have these browser APIs that are trying to connect with the native on-device CPU. So if you're using a laptop, of course, you cannot expect to run a very large model. So ultimately, it all boils down to the fact that you are confined or constrained by the amount of space and then the compute that you have. So in that case, yes, to answer your first part of the question, you would typically want to use a quantized version of the model. But as Apple has this hybrid approach where you could dynamically during the runtime identify those particular parts of the program that are perfectly suitable or perfectly suited for um, being able to execute locally. And then there might be certain parts of your workflow where you need to call upon a larger model. And in that case, I mean, you can still put certain guardrails. You could mask certain parts of your entire application at the application layer itself. Maybe like automatically detect passwords or environment variables and mask them before sending them to OpenAI or whatever LLM that you're using. So it's putting these certain guardrails for these LLM applications to ensure that none of your private information is actually flowing through. But yes, being just proactive and automatically being able to detect the parts which might need that hybrid approach of calling a cloud-based API versus being able to see, okay, like these are the workloads that do not require too much compute, so you can still uh, run them on device. Or maybe like another example is, I think an approach would be that you execute some parts of your code locally, and maybe once it has reached to a state where now you can probably share it on the cloud, because that hybrid approach could be dependent on the use case or the business requirement, right? But yeah, I would say like these are the two main recommendations.
Okay. From your demo that you did of all of this, were there any surprising results or any tips that just from building this that you would share with developers?
Yeah, I think so. The demos that I showcased, one of them is actually one of the most popular demos for the one that we also had a lovely interaction. You also got to meet Joshua, who is the author of Transformers.js. Now, I'll make a controversial statement here, and so like to say that Transformers.js is like the spiritual successor to TensorFlow.js because let's be honest, like as I mentioned earlier, also that TensorFlow.js right now is kind of in a maintenance mode. That means you can still use a lot of the models that are there, and they work very well. Like even with today's hardware and all of the different architectures, they work very well. I use them in production right now with the previous company that I used to work with, and they're still very capable. But with LLMs, they are not capable, right? So one of the examples was basically using this open source Whisper model that has been optimized with the help of WebGPU to run directly on the browser. That means the way that it actually runs is that uh, all of your input voice gets converted into the tokens, and then you create this pipeline where the input tokens are ingested, and then the model does the inference to convert them into the output tokens, which are the text because it's doing real time captioning. So, I mean, there's not really a lot of optimization there because the way that that pipeline has been designed and the way that transformers.js natively is, and that's what even Joshua basically does on a day-to-day basis. He takes these Hugging Face transformers-based models, and there are scripts that convert them into support for running with JavaScript, and then he writes the custom ops, which are probably like required to support web CPU. So I think like there's not much optimization, but the other demo which I showed was like how you can run this LLM model, which is I think like a Gemma 2 model. And one other thing that is also doing, which is interesting, is running this entire RAG or the vector search completely in the browser. So in
Wow.
that case, I'm so sorry, does this?
No, I just said wow. That's cool
Oh
that
yeah,
you can run RAG and vector search completely in the
yeah.
browser.
Exactly. So in fact, like if you look at IndexedDB, there is this database called RxDB, which can run a cosine similarity and the vector directly in the browser. So in
Wow.
that case, it's not like magic, right? We are using this. So for embedding, you can use this Hugging Face embedding model, one of the most popular models called Allman V6. You can now use transformers.js to load that model, and again create the embeddings or generate the embeddings for your input text thanks to that transformers JS model. Now, when it comes to storing these embeddings, you could store them in your indexed DB or your local store, and then the actual cosine similarity algorithm, again, that can run in the browser because that's just doing the compute. Now, the limitation here is that yes, you can't expect to work with 1 million different vectors. That's not we are recommending because the browser again has limited storage. So maybe if you have up to 1,000 documents, maybe it might work. And it's also probably not going to be very optimized if you have a vector with very high dimensions, like a 4096 vector. We specifically used the Hugging Face Allman V6 model because I think it generates 328 dimensions, if I'm
Wow.
356, 370 something. So that's still doable because at the end of the day, when you're doing cosine similarity, if you have much larger vector dimensions, then the compute also increases. But the architecture was very simple that the user uploads the document, you use the Pi PDF reader or not Pi. I was literally working with Pi. So, anyways, like you'll use a JavaScript library that can extract the text from your PDF, and then you use this transformers JS embedding model to take that input text first, chunk it up. So you take one chunk at a time, get the embeddings, and then store them into the on in browser database. And now when the user asks a new question, you convert it into the embeddings and you perform the cosine similarity. That cosine similarity algorithm also runs completely in the browser. And once you retrieve the context from the response from the vector search, now you just add that context to the local LLM that's running. So of course we have spoken on how you do that, whether it's with the WebAssembly backend or web GPU, and you pass that as context, and the LLM will stream the response. So yeah, I mean that was like the reference architecture of the application that was showcased during that particular talk. But the idea was that each and every step of that process you can truly like use browser APIs and browser technology like WebAssembly to your advantage. So even the embedding model, which is the Allman V6, that also actually downloads hyper specialized SIMD based WebAssembly binary that is what's being used to generate the embeddings. So that embedding generation process is also happening again with WebAssembly. So you'll see that there are essentially two different WASM binaries. One is for the LLM if you're using a WebAssembly backend, and then there's a separate binary that's doing the embedding generation.
Wow.
So if you were to look at the network calls, it will show you those two separate binaries.
Incredible. You mentioned cosine similarity multiple times. Can we explain that briefly? Like what is cosine? Why is that algorithm superior?
Yeah, I mean, if you look at vector, calculating vector distance, right? So ultimately, these are just points in a Cartesian plane. So you are calculating the distance between the two different points. Now, the most simple way to do is Euclidean distance, which is just simply taking the square root or the difference of the square root of the x Cartesian planes and then adding them to the y Cartesian planes and then taking the square root. So that gives you the distance between the two different vectors. And this way, we are able to compute that the vectors that have the smallest distance, that means that they are the most similar in their real world features. So similarly, like with cosine similarity, you are basically taking again, I might have to revise the exact formula, but you are essentially taking these distances that you have calculated between the vectors and you divide like between them. So you get this ratio. So this ratio would be that higher the cosine similarity between the values, that means they are more closely related to each other. That means that the distance between the vectors in the Cartesian plane is smaller. So the higher the similarity score between two vectors, that means the more real world features, they have more closely matching real world features. So that is why like cosine similarity is one of the most common ways in which we actually compute these vectors and the distance between them and how similar two vectors are. And that's a
Wow.
great way to tell you that how similar two things are in real life.
Thank you. I think that was maybe the best explanation of this I've heard so far. Definitely on the podcast, anyway.
Thank you so much. Yeah.
We've spent so much time talking about client-side inference, client-side vector search, client-side RAG, where your client is some type of edge device, as you say, or a browser. I'd love to shift a little bit and talk about the server side. You present, I think it was at Pi Ohio last year, right? You
Yeah,
did this talk titled "Serverless AI Inferencing Using Python and WebAssembly." Um, how 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 does that work? How do you use WebAssembly on the back end
yeah,
to deploy like ML code in a serverless? And I'm asking because ML ops is such a huge topic, right? Like the reason
yeah.
ChatGPT even made it to what it is because the team at OpenAI had this idea, hey, let's host this model and then do inference on the server side and like stream the tokens to the browser. Yeah, so how can one do that?
Yeah. By the way, I just hope that you're not hearing some background noise. It's probably the air conditioner.
Yeah, no, I do hear some horns in the background, but it's okay. It's not going to be disruptive at all.
Oh, perfect. So, yeah, sorry for that. Yeah. So the main thing here is, so as I mentioned earlier, that you can people realize that as soon as WebAssembly saw a lot of you know adoption within the JavaScript landscape on the browser, people question that, hey, you have this really tiny way of being able to take your source code, convert it into the binary, and then run it in such an optimized manner that because the WebAssembly binary has such a small size. So they said that at on the backend side, we are dealing with these large scale containers that can be hundreds of megabytes. They have to deal with a cold start problem because it can take a few minutes to even just invoke and kick off a container, right? So one of the problems here is like service functions is Lambda. Now, a Lambda function, depending on what runtime you're using, like it's a Python or Node.js based, under the hood it's using a container, and you're spinning up a container. You're waiting for some time for the container to completely get turn on, and then now you will be able to run your serverless code. So we saw that, okay, like because it has a capability to run this optimized code and still take up a lot very small space, how can we also bring it into the cloud and the server side environments? And that is where we were having this discussion that yes, there is a common misconception that you can only run WebAssembly with JavaScript, but that's not true because you have all of these other different WebAssembly runtimes that can run your WebAssembly code for you, whether it's with a like Python or with Golang or Rust, right? So you have runtimes like Wasm Edge, which is optimized to run with the WebAssembly modules in a edge environment. You have Vaz0, which is a WebAssembly runtime that is optimized specifically to take your Golang code, run it or convert it into WebAssembly binary, and then run or execute that WebAssembly binary with the Vaz0 runtime in cloud-based environments. Or there were specific optimizations made on the container specification itself, right? So if you look at how containers typically run, you create the image, you create the container, and now let's say you're executing it in Kubernetes. So you have a Kubernetes cluster, you have a pod, and you run the container inside of the pod. And the way that it runs it is, so if you look at this, the architecture for that, so you have the pod and there's a container runtime. So that container runtime is responsible for executing whatever is there inside of that container. So there was a specific optimization made or a feature that was implemented to also support running WebAssembly workloads alongside your container workloads inside of Kubernetes. So at the CRD level, which is I guess like, so if you look at how container works, again, this is like probably diving deep into it. So you have the container runtime, but you have cryo, which is like you have these custom resource definitions, so CRDs. You add support for uh, WebAssembly over there. So now you can actually run WebAssembly workloads in parallel with your container workloads inside of Kubernetes. Um, so that was one of the ways in which, and in this case, what you're actually doing is that you're also shipping the WebAssembly runtime because you cannot just directly run the WebAssembly module. You are basically shipping the WebAssembly runtime and the WASM module, and now it can execute inside of your Kubernetes node. Or maybe the example that I showed for my talk that I gave at Pi Ohio. So that was there is this open source project called as Fermion Spin. So the Spin allows you to uh, run serverless WebAssembly. So you have like, let's say, a lot of functions in JavaScript and maybe in Python, in .NET. So the Spin project has different SDKs in languages like .NET or C Sharp. So it will be able to compile that code into the WebAssembly module. And then the way that is like, let's say you have 1,000 requests. So for each 1,000 requests, typically you would have to spin up a serverless function, so that will take some time, and then it will run, and then you'll have to wait for your container to close. But with
Mm.
WebAssembly, you can imagine that you have 1,000 requests coming at the same time. So for each of these 1,000 requests, you compile the code into the WASM binary. Now you just spin up that WebAssembly binary when you want to execute that particular function. It Because WebAssembly binary has a much smaller size, and the cold start time for actually invoking a WebAssembly module is way smaller as compared to
Mm.
containers. So it instantly just spins up. You execute the code and you kill the WebAssembly module that you have just created. So this way, you can imagine that when you're scaling up workloads where you have millions of requests. So with the spin project, you can spin up, right? That's how they came up. You can spin up millions of these WebAssembly modules, and during the time of execution of the function, you just have to spin up the WebAssembly module over there, and it will execute the function, and you then kill the WebAssembly module. So this also becomes a lot more cost effective because you are now freeing up your infrastructure resources, and they are only needed when you're actually doing some type of inference or you're executing some function. So my talk was primarily around that: how do you leverage Spin, and how you create these serverless workloads, so that whenever it comes to actually running a serverless function, only during that time the WebAssembly module will get invoked. So the WASM module will be used to do its inference, like whatever it's executing, whatever task has been designed, and then once that function has stopped executing, then you can just kill off the WebAssembly module and free up your space for like freeing it up. So you also become much more better when it comes to being able to use your system resources more efficiently, rather than having to continuously run these containers over time. You save up all of that time and space. So that was one of the reasons why we saw that adoption, because of the small cold start time in comparison with containers. And at the same time, uh, one might realize that containers have this issue that when you design like a container for Linux, you cannot expect it to run on a Windows machine. And like probably a container that has been designed to run on a X8, X86, X84 architecture, X86 architecture, my bad, X86 architecture, that same container might not run on a RISC-V device. But with the WebAssembly module, it is platform independent. That means that that same module can run across different device architectures. So it also allows the application developers to not have to write optimization code to be supported across different types of device architectures. So that is the reason why WebAssembly saw such a huge rise in adoption on the serverless side of things, and also on the container and cloud side of things.
Mm. So if we follow the example we set out to do with the client side discussion, for example, I'm going to go to Hugging Face, I'm getting a quantized model, and I'm doing inference with Onyx or TensorFlow.js. Can I do that on the server side? Can we talk about a step by step of
Yeah,
how a developer can get started to create an API only AI inference app? Similar like ChatGPT, Claude, all of these things
exactly.
you can leverage them via API and build AI apps with them. If I wanted
Yeah.
to, in a way, build my own AI inference over API, how would
Yeah.
we do that step by step?
Yeah, absolutely. So you would, of course, start off with your native code that you have written in, let's say, Python. Uh, and if you're specifically talking about the edge, then Rust, surprisingly, Rust is a very popular language for being able to run performant uh, machine learning code. So, in fact, there are not a lot of people talk about it, but there are a lot of libraries that are also supported to run with Rust. In fact,
Mm.
like MediaPipe or even PyTorch, they have specific libraries that you can run with Rust, because again, this is probably up to debate, but in some scenarios, Rust is more performant than Python. So whether you're taking a Python-based model or you have written your model code in Rust, the first step would be that you would convert that particular inference code into a format for WebAssembly. So with Rust, it would be a simple Rust up cargo build or cargo up. I forgot the command. I think it's cargo WASI32. So there's something in between cargo, and then you
Right.
specify the WASI32. So that's the WebAssembly format. So it will take your Rust code and you will the output would be a Rust. It will be a WebAssembly binary, right? And now you can execute that WebAssembly binary with any supported WebAssembly runtime. So like Wasm Edge has great support for most of these Rust based machine learning libraries. It also has support for PyTorch with Python. So again, breaking it down to step by step, you have your application code or the inference code written with a PyTorch framework or like let's say with a any other framework like TensorFlow. So you convert that inference code into WebAssembly, and now when it let's say that you want to create an endpoint slash predict or slash completions API. So now what would happen is that you have this WASM binary. Um, Now you would take wherever you're running your application, you'll also now install and run the WebAssembly runtime in this case, because in this case we're not using JavaScript. So depending
So
on
if,
if you,
if we're hosting this, say on like AWS EC2, Fargate, something like that, we
yeah,
go into our cloud instance and we add the WebAssembly runtime.
exactly. So you
Okay.
would download and install the WebAssembly runtime, and whenever it comes to let's say now you're making that prediction, you're calling that API, the WebAssembly runtime will execute the WebAssembly module for you and that inference code in this case, and you would get the results. So that's like one of the key differences when it comes to comparing how that execution looks like on an API front with the backend versus your JavaScript. Because if you
So the WebAssembly runtime could also just be Node. If I, for example, if I'm on EC2, or if I forget EC2, if I just have like a server, I
yeah,
SSH into the server, I installed Node, I write a little JavaScript script that initializes this WebAssembly module, receives input from the network, so like an incoming network request rec.body, right? Maybe it's a JSON request with I don't know input as the parameter. So I take that and I send it to the WebAssembly module that I've parsed in JavaScript, that I've initialized in JavaScript, and then the WebAssembly module gives me the inference, and I just send that back over like res.send,
this that's it.
inference. Is that
Yes, I mean there are some other things also happening behind the scenes, but if you talk about a very high level architecture, that would be like of course the very high level architecture. But there are certain things that also go on behind the scenes, right? So let's say that, and the reason I was saying that you would need a dedicated WebAssembly runtime is that it has to be supported with that particular language, right? So if you are saying that you have a Go server, right, or even a Node server, like let's probably talk about a Golang server. So you still have to execute Golang, right? You're still executing Golang code on the server. So in that case, the WebAssembly binary that you created. So let's say in this case you are using var0 as your WebAssembly runtime, which has been specifically optimized to run with Golang code. So in that case, when the request comes to you from the user as the request body. Now you would take that API code, which was originally written in Golang, and now the WebAssembly module will kick off the execution, and whatever application inference or whatever type of function it's supposed to execute, it will execute that, and it will return the response back to you, and then you send that back to the front end. So depending on the type of language stack and the WebAssembly runtime that you end up using, that would what makes it dependent on what was that original language code in which you wrote the WebAssembly. Because maybe like because that's just a high level thought that yes, in theory you could also just have a Node.js server and execute it, but the WebAssembly runtimes they bring in some optimizations. So things like ahead of time compilation. If you want to make your application code much more performant and you want to just ever so slightly improve the performance. So a lot of these WebAssembly runtimes, they have optimizations that they can make, whether it's like how we have just-in-time compilation with Node.js. So if you want, in certain use cases, you want faster executions, you want to execute AOT. So like Wasm Edge has a specific mode in order to execute WebAssembly with the help of the Wasm Edge AOT. So it will use that ahead of time compilation to execute Wasm modules, and that will make the performance even faster because you'll be able to run the execution of the Wasm module, and whatever code you're running as part of the logic, it'll be able to run that much faster thanks to AOT. So you get some of these customizations when you run a WebAssembly runtime. Because another way to also look at this is that like WebAssembly itself, right? The module itself cannot do anything for you. It's just a simple black box. So in fact, like if you were try to make a network request, you can't do that. So that's where the WebAssembly runtime actually comes into the picture, because the WebAssembly runtime is supposed to have these capabilities such as making network calls, making file system calls. So if for some reason you are creating a new file or you're updating a file, those are being handled by the WebAssembly runtime. Now, yes, if Node.js can handle all of that for you, yes, you can use that. But using a dedicated WebAssembly runtime will give you a lot more benefits, because if you're dealing with like garbage collection or you're trying to debug a WebAssembly module, so these high-level software abstractions like garbage collection, debugging, or maybe you are talking about file system access, network access. These are being handled by the WebAssembly runtime and not directly by the WebAssembly module, because it itself cannot do anything for itself. So similarly on the JavaScript side, like JavaScript is what's taking care of handling all of that. So I hope that answers the question. Yes.
Definitely. So let's summarize. We've covered so much, which is so cool. I mean, a lot of it is, I'm sure, first time knowledge for a lot of people, and they've often wondered like, how does all this work? And you've provided insight into that. I'd love to say like a sentence summary of everything we've discussed so far, and I'd love you to either confirm or ideally elaborate, ensuring that the junior devs among us would understand these things. So this is what I would, if I summarize everything we've discussed in like one sentence, it would be: for a developer, using WebAssembly, especially for AI, means no server costs, or maybe limited server costs for inference. It also means better privacy, so you don't leak data to a model, and you can use languages that are familiar to you. You don't have to use like Python, but you could do Rust, you could do Go. Is that right? Can you maybe confirm
Yes.
or elaborate? Did I miss something?
No, no, absolutely. You didn't miss anything. So you can really just write your code in any language, because you have machine learning libraries even for Java. So technically, you could also compile a Java code. So yes, depending on whatever language you want to use, there's no limitation, right? Whatever language today has support for being converted to a WebAssembly module, you can use that.
Fantastic. What are some things that developers could build with all this today, like TensorFlow.js, even Onyx.js? What are some things they can build today that would maybe surprise people?
Yeah, I think the one of the things that surprises people every time, and I have been giving talks about TensorFlow.js probably since
Yes.
2021, right? So it has been one of my favorite topics. So uh, even today, like when I gave this particular demo, a lot of people came up and asked me that, wow, you can actually do that with the browser. You can do that on JavaScript. Because even today, I would say, I'm just probably making this up, but probably 80% of the JavaScript developers in the world don't realize that you can run machine learning with JavaScript.
Right.
So every time I gave a talk, even in 2024, I gave a talk in front of 120 people. Out of those, only 20 people knew that you could actually run machine learning code with JavaScript.
Mm.
So that's still a wow factor. So if you're a JavaScript developer and you want to build and incorporate some type of machine learning application, you can still use the simple models that were created 10, probably like 7, 8 years ago. They're still usable. And you can also run LLM inference on the browser. But at the same time, I think when you look at the edge space, people often realize that yes, there is so much pain point trying to reduce container sizes, but a lot of your application code could be run with WebAssembly. And because of the cold start time, smaller memory footprint, like smaller size of a, if you think of a WebAssembly model as a container. I love to show this particular slide. If you take a MobileNet model that runs with a PyTorch container, that would be about 400 megabytes in size. The same MobileNet model, when it has been converted to a WebAssembly binary, is sometimes like it's like 1/10 or even 1/20th the size.
Wow.
Yes. And if it took 1 second to run inference with the Python code in a container, it was again half or 1/10 the time or the inference time that it took to run it with WebAssembly. So
Amazing.
when you get those type of performance benefits, that's where the true value of WebAssembly like shows up, and that's like a wow factor.
Mm,
So
amazing. Thank you. Yeah,
yeah,
yeah.
and
Go
I
ahead.
just wanted to like probably talk about like one last thing. So we spoke about
Yeah.
that spin project, which allows you to run serverless code with WebAssembly, right? So
Yes.
imagine now running a workload that sends 1,000 API requests. You're running that same with an AWS Lambda function with Python, versus you're running the same with a spin-based serverless workload with WebAssembly. So the amount of latency, or maybe like the total time it took to execute, maybe you're capturing all of that, right? You'll again see a huge difference in terms of how quickly you're able to actually run all of those particular tasks in parallel, and the sheer amount of um, time it takes for it to run with a container workload with with Lambda function will be a lot higher. So those are some, I guess, like some of the wow factors.
Yeah, thank you. So the whole point of this podcast is to sort of empower developers everywhere. And so particularly ones who are like completely new, right, to these kinds of fields. And I think there's a lot of people, man, honestly, there's people who are like senior, maybe staff level, like web UI engineers who have never touched machine learning. And so a senior there could be a junior here, which I think is so cool. And so for
Yeah.
these developers, like let's say a web developer, no matter what experience level, but they have zero ML background. I'm curious, what would you say is like the learning curve if they just wanted to add either image recognition, so like maybe an NSFW detection, or maybe something closer to home, text generation. So like I send you a prompt, you send me a response. If they wanted to add this feature to their app just with TensorFlow.js, nothing more, how would you describe that learning curve?
Yeah. Again, that varies because, as I described earlier during the podcast, that TensorFlow.js gives you three different learning paths. A
Right. So
is that
let's wait. Let's talk about the easiest, like
easiest. Yeah.
lowest effort. Like I literally I've never touched this, and so obviously you
Yeah.
wouldn't want to start with like the more advanced learning path there.
Exactly. Exactly. So that's what I was also starting off with. So you have these pre-trained models. So we call this as pre-trained models, which are already trained for you. So you don't need to learn about the technical jargons, such as what is even training, what is pre-training. These are models that are already available to you, and you just have to literally run one line of code, which is model.predict. In that
Wow.
predict, if you're using image recognition, you literally just pass the image itself, and that's it. You'll get the response. So this means that the only thing that you need to be aware of is that yes, there is a MobileNet model and it does image prediction for you. And you just probably need to be also aware of that what are the type of different labels or the categories of things that it can actually detect. Because if you give it probably some material that is not even developed during the training of this model, it will not work. So it, I think, is able to classify approximately 100 different types of objects. So you just need to be aware of that. That's it. You just want to know that there's this machine learning black box, and I just need to use the model.predict function, and I'll get my response. That's it. So as a UI engineer, as a JavaScript engineer, you don't need to learn about the technical jargons, right? So that's the
Yeah.
lowest level.
Okay.
While barrier to entry is greatly reduced, there are some limitations to that. The biggest one being that you are limited by the total number of images, classes that you can actually classify. So if you were to expand the number of classes, maybe because if you look at the most common classes in the ImageNet model or a MobileNet model, they are usually just some images of some hot dogs or cat, dog, like these type of very basic objects. So maybe if you're running a company where you have a lot of industrial goods or industrial tools, and you want to classify and be able to detect what is this particular tool, right? Maybe
Yeah.
your operator comes across this new tool and they don't know how to operate it. They don't know about its name, so they click a picture of it and they want to get to know what is this particular tool. Now your off-the-shelf model will not simply work. This is where you'll have to use either what we call as transfer learning, or you'll have to retrain this particular model with a new data set. Now, yes, these are concepts which are completely alien to the JavaScript developers. But that being said, with TensorFlow.js, now one step above is what we call as transfer learning, which means that you already have your model, existing model, and you give it a new data set, and the model retrains itself or updates its model weights by taking input all of the new data that you have trained so that it's more optimized and has been retrofit to run well with your custom training dataset. And for this also, there are specific UIs that can actually automatically do this for you. So there's something, this was a project opened by Google called as Teachable Machine, where you just upload all of your images or whatever data, and it does this transfer learning process for you and gives you now a new model that has been retrained with your data. So even here, you don't need to learn the concepts of what's retraining, what's transfer learning. You just need to know that, yes, what's your data on which you want the model to work well, and you'll be able to then you'll also get generated code that you can just run locally in your application. That's it. And the third is that, yes, if you are a machine learning engineer or you are a JavaScript engineer who is learning about machine learning from scratch, then you also get these really low level APIs where you can even design your own simple machine learning model and train it and then run it with JavaScript. So as a JavaScript developer, you have all of these options.
Fantastic.
Yeah,
Thank you. I love that there's something there for everybody.
exactly.
We've talked a lot about client side inference. We talked about server side inference. We talked about how people can get started. I think the only thing we haven't talked about is explicitly hardware. So
Hardware.
a lot of software, but not hardware. And the cool thing about WebAssembly, as you mentioned, is it can run on a variety of architectures, a variety of hardware architectures, even edge devices, so to
Yeah,
speak. But I'm very interested because, like, in preparing for this episode, I saw that you wrote this thing where you looked at this blog post about Grok's fast inference, and you tied it into your job, Couchbase Vector Search. But I'm
yeah,
curious, this specialized AI chip that Groq makes, is its performance is pretty incredible, right? It's
pretty incredible.
significantly faster than OpenAI and Anthropic, etc. What should developers know about these sort of emerging hardware options? Does it affect people day to day? Should I be coding for Grok's specialized hardware, or should I just be making things that work across a variety of architectures, like you mentioned with WebAssembly?
Yeah, I think that I'm always in the this type of ideology that whatever you build, it should always be accessible to everyone. You should never
Mm,
build a platform that's constrained to only run for a certain set of users. So maybe that's one of the reasons I don't always agree with Apple's mindset. And I know,
yeah.
like, a lot of people in this world, they do not. They just succumb to either the peer pressure to get into the ecosystem because everyone around them is using that. So maybe, like, that's probably a discussion for another time. But yes, I like to work on software or applications that can run universally, right? And that's why, like, I really got into the WebAssembly ecosystem, because the ethos for WebAssembly as a runtime is that you
Yeah.
can take that same code and run it across different architectures. Now, to answer your question about, okay, should engineers be designing applications to run for certain type of optimized hardware? I think that depends on the kind of workload. So maybe, like, if you look at Grok specifically, the main reason that why today companies like Google with their Tensor chipset, right? They gave up using Qualcomm chipsets and they started to design their own in-house Tensor chipset in their Pixel devices or their tablets. And in the future, they might also release Chromebooks with it. You never know. Um,
Yeah.
and the reason why Google years ago they launched the Tensor Processing Unit, which is the
Yeah, the
TPU.
TPU. Yeah.
Exactly, which are highly optimized to run deep learning workloads that have been built upon the TensorFlow framework. Now, does that mean that GPUs are bad? No, they're not bad, right? You very rightly mentioned yourself that when it comes to parallelization, you can run multiple parallel threads and execute your mathematical functions thanks to the CUDA framework. So because they saw that when it comes to their use case, it was very much optimized, and maybe like they were not very happy with the open-ended architecture of a GPU. So they went kind of from ground up designing their own chipset and the architecture of the chipset. I think like similarly, I was reading an article or probably like a video where one of the Grok engineers they were sharing the thought that there was this massive divide, like when it came to LLM inference and maybe like how CPU or the existing GPU architectures were not necessarily optimized to run some of the compute that's specific for these transformer based models. So they and in fact, like if you look at the leadership at Grok, a lot of the principal engineers are actually people who worked on things like TPUs at Google. So they have had the experience of like building these custom chipsets that are very well optimized to do one set of things. And that being said, there's nothing wrong with it. But at the same time, if you want your code to be able to run on what we call as like open platform, right? You want to use a technology like WebAssembly. Um, so yes, if a company has like a dedicated use case, they wanted to create a niche where they say that as compared to every other model provider and inference provider, we will provide the fastest inference. And to a certain extent, like you can look at Grok's inference speeds and they have really optimized it. But at the same time, now it's very limited, right? You cannot just take your own hardware. You cannot request Grok company that if you are a privacy focused company, you cannot like ask them that, hey, we want to run your Grok's inference on our own hardware. Like you still need to use Grok's custom chipset that they have designed. So that means that now you'll have to maybe like if they have an enterprise plan, that company will have to take that custom designed chipset from Grok, install it in their local infra, and then run that.
Yeah.
It's not open, right?
Yeah.
So I'm probably of the thought that we can still maybe like okay, you cannot beat the TPU performance or the Grok's custom chipset performance, but you can still get very close to it because every single day, all of these GPUs are getting better. They are a lot of the custom chipsets that are being designed. They're having AI native functionalities, or like the way that these chipsets are being designed. They have AI capabilities that you can run the inference way more faster, right? So they are being optimized. It's not like Qualcomm and all these companies are like sitting ducks. They are actually working on improving their architectures to support AI workloads. So I
Yeah.
would probably feel that there would be a time when they'll be able to catch up with these hyper specialized chipsets.
Mm. Yeah, that's okay. So it sounds like the general advice is just be careful and know where your audience is going to be, right?
Yeah,
And like, and also I guess I love the privacy concern you raised for companies that want to maybe run those fast inference workloads, but on their own hardware, which they can't do
exactly.
right now. Yeah. All right. Hey, I have maybe one last question for you, which is you did a comparison. You did a comparison on inference speed, and you compared OpenAI, you compared Gemini and Grok.
Yeah.
What did that tell us about that?
Yeah. So that is like pretty simple. I literally started to take the network speed at like, or not network speed, but basically I started a timer as soon as you make the same request and compared running it for OpenAI, for Gemini, and then similarly for Grok to look at the total amount of compute and trying to keep the rest of everything same. So that means that
Hmm.
probably like trying to use a different, like similar type of model. Now, of course, you can never have a benchmark that is absolutely, clean or probably balanced. But I just try to make sure that I use that. And I'm not claiming that that's probably the best benchmark. Probably it's a very high level benchmark. But the reason I wrote that blog post was that I was actually blown away by the fact that, hey, Grok is this new, and by the fact, this for matters that that blog post got published 7 months after it was written.
No, I see.
So
Okay.
it's not that I got to know about Grok like this literally in December last year. I got to know about it probably in like whenever they were launched their first ever version and they were launched in private preview. But at that time, I was genuinely impressed by their performance. And I was just comparing, okay, from start time when when the user hits enter and you send in those input tokens to the LLM and it processes it and generates the output tokens and the text. So just comparing between those two and getting the result. So I know it's probably not the most ideal benchmark to compare the speed or the performance, but looking at ever since then, a lot of the other benchmarks that have been run, at least for quite a lot of workflows or workloads, Grok's performance all is way better. And see, ultimately,
Put a number there. What, like 2x, 3x, 10x?
not
How
2x
much better?
actually. So it would like probably be 1.1x, 1.2x.
Okay.
So, and again, like I know I never like to say this that it depends, but it might depend on the kind of workload that you're having. Maybe if you have images data or you have millions of text documents or PDF documents, the way that even your data is structured, maybe that might uh, influence how much faster Grok is for
Yeah.
certain workflows. But in general, like if you look at just a very high level picture, yes, in general, it will be slightly faster in terms of inference speed as compared to the typical model providers.
Fantastic. Well, hey, listen, Shiva, I have so much more that I want to talk to you about. I mean, this is all the technical side, but you're so active in the community. You know how to talk to. You speak at so many conferences. You're active in open source. You mentioned you contributed some op. There's like we should maybe do a series, but I think we'll leave it here for the sake of the attention span of the listeners. I mean, we covered so much. I mean, we talked about software. We talked about WebAssembly. We then talked about server side, and finally hardware. What a tremendous wealth of information. I know it's maybe challenging to sit and talk for so long, but I so appreciate your effort and the value you've added. So on behalf of myself and all the listeners, man, thank you so much for coming on and sharing all of this with us.
No, absolutely. I love that. And maybe like, in a future podcast, we could talk about DevRel or communities. And I know like we wanted to talk about RAG. I know we covered RAG. So maybe that could be a separate discussion. But again, I really want to thank you for inviting me. I know like we have been great friends and we have been meeting, but this kind of a setup is catering to a very different audience. Like this is for people who want to really dive deep into a particular topic and get to know about the nitty gritties that they might actually not find on a blog post or in some documentation, right? Because and I've seen this like with the podcast that you did, the most recent one with Dev as well, where he
Yeah,
spoke about signals and how solid implements that. I certainly feel that a lot of the conversations that people hear on this particular podcast, on the Quantization podcast, is not available on the internet. It's just in this podcast, and there are so many small nuggets of information that are super valuable. So again, I'm so humbly thankful to you for doing such a great job and being consistent with it. I know like it takes probably a lot of effort on your side as well. You have to kind of do that research and get into the shoes of that other person and have that discussion with them. So I know it takes a lot of effort. So huge kudos to you as well with all of your travel and work as well. So yeah, thank you so much.
thank you for joining my discussion with Shivay Lamba. I hope you enjoyed it as much as I did. Shivay is such a wealth of information, and he has so much to say. So if you'd like to continue to follow up with Shivay, his links to his social media are down below in the show notes, as well as other materials he referenced. Feel free to follow him, tap him, ask him your questions. He is here for you. If you're learning from and or enjoying this podcast, a great way to support it without any cost to you is to leave a comment on the platform you're at, whether it's YouTube, Spotify, or Apple. If you want to leave any review of the podcast, up to 5 stars on your favorite podcast platform, that would also help. But I think the thing that would help the most, honestly, is if you just share this with social media, maybe clip it, share portions of it with your friends. If there's anything of value here, then the best thing you can do with value is share it. And coincidentally, by sharing that, you also support the podcast. So I hope that gives you some options. Of course, if this wasn't useful to you, then also make that known, maybe. In any case, thank you so much for being a part of the podcast. Thank you for being a part of this episode. And most importantly, thank you for your interest in engineering.